Hi, I'm Antonio Oliver.
And my name is Cameron Reed, and together we worked on our EET Senior Design project, which was wireless headphones. What will be included in this project is why we chose the project, brief history on wireless headphones, basic transmitter and receiver components, testing and simulations, problems and solutions, and the conclusion. There are many reasons why we chose this topic. One is the challenges presented to previous students in previous years on this project. Another is personally my passion for car audio and music. A third being the growing trend of headphones on campus and the cords that are always in the way, whether it be in the gym or getting stuck on your book bag. Lastly, for a better understanding of wireless transmission.
I'm going to discuss a brief history of how wireless headphones came about. The creation of headphones was an idea branched off the telephone, which is accredited to Alexander Graham Bell on March 10, 1876. His idea came from an improvement making the telegraph. The first speaker was made up of metal diaphragm with a paramagnet. A paramagnet is a substance in which magnetization is proportional to the strength of the magnetic field applied to it. John Cost and Martin Lang were the first to produce musical style headphones. They were stereo style and people were amazed by them. I want to now discuss the technical components of the transmitter. Here we have a 900 megahertz or 916 megahertz antenna. It's from Lynx. Here is the transmitter module we use, which is a 900 megahertz frequency, connected to a dip switch, which is 4 pins, and we only use 3. Here's the capacitor from the data pin going into our amplifier, and the amplifier we used was a TL3472. It's a dual op amp, and we also purchased it from Lynx. Here we have 2 battery sources, a 9-volt battery, one to power the op amp and one to power the pin. We have to use 2 battery sources because op amps have a negative power and a positive power. These are the battery connectors. Also, we have a 3.5 millimeter phone jack, which can connect to any audio output such as MP3 player or iPod. A major component of the board was the ground plane. At high frequencies, perforated boards just wouldn't work for the high frequency we wanted to use of 900 megahertz. As you can see here, the ground plane is a type of prototyping we use that utilizes the Manhattan construction project. Chips are flipped upside down or upright and glued directly to the board. Since we had so many grounds, we didn't want the antennas to be interfered with strenuous spaghetti string wires, so we hooked everything to the ground plane to prevent impedance. So, as you can see close, the amplifier chip is flipped upside down and bent. All the pins are bent upright. The module was directly placed on the ground plane. We basically glue every component to the board so it would be sturdy and have low impedance. Each pin chip, by using the ground plane, each capacitor could be directly fitted on the chip where it needed to be.
My portion of the project was to do the receiver. Here on the receiver, as stated before, just like the transmitter, there's a 916 megahertz antenna connected to the appropriate SMA connector, as well as the RXM 900 HP3 series receiver. Connected to that, we have a 4-pin dip switch, which only 3 are connected in order to choose the appropriate frequency to communicate with the transmitter, as well as a potentiometer to be able to adjust the volume, and a phone jack, the female part of a phone jack, in order to hook up any type of headphone with the 3.5 millimeter, the battery connector, a 9-volt battery in order to power up the circuit, as well as the Singapore double throw switch in order to turn on and off or to allow power to get to the circuit. Also here is a speaker which is left over the remainder of old headphones, which can also be used as an audio output signal from the, what we have, LM386 audio amplifier. As previously stated, the audio amplifier that we decided to use was the LM386. The reason is because it is a low voltage audio amplifier and it can be used in many applications such as AM, FM radio, portable tape players, intercoms, and TV sound systems. As well, in addition, we use various capacitors and resistors for filters, and of course the ground plane, which is used in the transmitter.
Now we will be doing a test simulation. iPod, 3mm jack connection. First, we want to play the music. Music from the iPod. Next, we'll hook the batteries up. Flip the switch for the receiver.
Then I'll be hooking the one 9-volt battery up to the receiver and flipping my single pole double throw switch as well. Well, first I'm going to be putting in the headphones into the 3.5mm phone jack, and then I'll be flipping on the switch. And now you're able to hear the audio that was once coming from the iPod to the receiver. Now, in addition, we also have the headphone speaker as well that came from a traditional over-the-head headphones. And once I turn it on and touch the ground, you should hear sound as well.
The transmitter works by taking the digital signal from an iPod and transmitting it through the transmitter, through the antenna. It's modulating the signal and sending it to the receiver to be demodulated.
Once the signal is demodulated through the receiver chip, it is then sent an analog signal to the speaker or headphones.
Now I wish to show the testing simulation on how the chip and the ground plane, all the components work. We have the antenna, which is on pin 2 of the module, and I'm going to test the ground plane connected to pin 10, which is going to use FSK modulation. It's a digital modulation, and the square wave with sending the square wave sending the signals using the 0 and 1s will be shown on the screen. First, I'm going to connect. We'll play the song. Now, I'm going to hook up the oscilloscope. This is going to go to pin 10. This is going to go to the ground. You should see a square wave displaying multiple 0s and 1s changing throughout the signal. You can see the waves it's not a complete square wave. It's going to be a square wave with little dips in it, sending the 0s and 1s to the antenna, which is operating on 916 megahertz, and that's the correlation to the chip pins, which is 101 on our data pin on the dip switch. If you can see, the signal is jumping because it's every bass and beat, it's intensifying. So that's why it's jumping and coming out. But you can see it's sending 0s and 1s with the FSK modulation to the receiver.
Now I'll be showing you a visual that to prove that the transmitter is actually sending the signal to the receiver and the receiver is actually accepting the signal. First, I'm going to hook the red and the black lead from the oscilloscope to the receiver. The black lead going to the ground plate, which represents ground, and the red going to the audio pin on the receiver, which is pin 17. Next, Antonio will be hooking up the iPod to the transmitter and pausing it and playing it, and then also using different volume variation to show the noise in the signal that is being received from the transmitter.
Song.
As you can see, now Antonio has plugged the transmitter up to the iPod and the switches are on. As you can see, there's what's supposed to be a sine wave, but due to the various wires on the receiver and poor soldering technique, there's tons of noise shown in the oscilloscope. Now we're going to play the audio while pausing and playing and using different volume variation to show the response on the oscilloscope. As it paused, you see the signal died out. Now once he press play, you can see the signal coming back again. As you can see, when he turned the signal on, when he turned the iPod on, the signal came back immediately. Now he will raise the volume and lower the volume to show the different noises on the oscilloscope. When you turn it down, you see the signal change or fade it out. When he turns it up, you see the signal came back as well. In conclusion, as a whole, the project was mainly a success. As far as being able to transmit an audio signal and being able to be gained through the receiver. The only downfall was that the signal was not very clear, meaning there was a lot of static. Wireless transmission is mainly used for convenience. In addition, more importantly, wireless headphones were designed for pleasure and leisure.
The goals met in this experiment were pretty successful. We took the transmitter and transmitted a signal to the receiver and displayed audio sound. We were not 100% efficient. We were supposed to do static-free, clear headphones, but they weren't static-free. They had a little bit of static in them. The references we used were Dr. Lawrence. He prescribed the ground plane method, and Electronic Communications Principles and Systems book, Fundamentals of Resource Allocation and Wireless Operational Amplifiers, Integrated Circuits book, Lines and Fields Electronic.
After completing this project, not only do we gain experience about wireless communication, but we also gain knowledge about different soldering tips, in addition to feeling more comfortable with other wireless applications in the future.
Our design as well, we have gained experience in designing our own specifications and testing equipment, and we now feel confident with doing other jobs in the future.